All right, so we're going to look at converting between Kc and Kp. So this is the politically correct equation, I like to call it at least, okay? Because P always goes before C there, so PC, politically correct. It's not on your yellow sheet, so it's not like a super important equation or anything like that, but you might see it on like UT homework or things of that nature. They pop up every once in a while, but it's nothing major by any means. So the biggest thing about this equation that would be kind of a little weird to you is going to be the delta n here. Bless you. Okay, it's going to be delta n, and that's always going to be products minus reactants. Okay, products minus reactants. All right, in terms of moles of gas. So, but it's products minus reactants. So they got this -1 here for that because it's equal to 2 minus 3. Okay, so 2 moles of gas on the product side, 3 moles of gas on the reactant side. That's how they're getting -1. And it's only for moles of gas. Only for moles of gas. You don't worry about any of the other stuff. Okay, only for moles of gas. All right, so in our example problem for this, they have us calculate for Kp. So once again, I'm just going to write the expression and then plug in the values. So we've got pressure of NaCl squared, products over reactants here, P of NO squared times the pressure of chlorine gas. Okay, and then we just plug in the values. So 1.2 squared divided by 5 times 10 to the minus 2 squared, and 3 times 10 to the minus 1. Well, I ended up getting 1920. 1920 there. All right, so then they want us to calculate Kc for this as well. So all we need to do is use our equation here, okay? And what we want to take a look at is the delta n, right? Delta n in this case is going to be equal to, how many moles of gas do I have on the reactant side? 3. And we have 2 on the product side, so products minus reactants equals a -1. All right, so then I just plug the values in here for our equation. And R and T are always in units of Kelvin, right? R is always going to be in units of atmospheres there. So Kp is 1920 that we just solved for. We're trying to solve for Kc. We have 0.0821 times 298, right? Because we're at 25 degrees Celsius, so we got to have degrees K. And we're raising that to the -1 power. So I got 0.0408 there. And 1920 divided by a second answer. So Kc I got equal to 40, pretty much 47,000. Is what I got. Okay. We okay with that? So it's just an equation to be aware of if you got to convert between Kc and Kp. It's not something that comes up a lot, but I think there's 1 or 2 problems on the UT homework where you got to do that. Okay, but I don't think this is something. This equation is no longer present on the equation sheet that AP gives you. So I think it's going away, and I don't recall it being on the AP test last year, but it's kind of one of those things like there's no guarantees that it might not show up. So that's why we're checking it out now. Not that you'll remember it then, but I don't know. Well, whatever. Okay, on to the most important part of today, which is this stuff right here. Okay, this one, we talked about magnitude of K yesterday, so that's just something to be aware of when you're looking at K. Greater than 1, products favored, less than 1, reactants favored. But the reaction quotient Q. All right, so Q is really what Q is doing for us is Q kind of gives us a snapshot, I say. Snapshot of the reaction. It identifies reactions not necessarily at equilibrium or not. Okay, so it's just kind of giving us a snapshot of where the reaction is, and it will help identify which direction reaction will move to get to equilibrium. Okay, so we don't know where the reaction's at. It could be initial, it could be just a midway point. It's just an idea of where we're at, and then we're going to, depending on which, how Q compares with K, all right, which way the reaction is going to go. So we're going to take a look at this stuff right here. This is going to help us out. All right, so we want to compare K and Q to one another. Q and K you calculate the same way. They're no different from one another. Just K is when we know it's at equilibrium. Q is we don't know. We have to calculate and figure out where it's at. So if you compare them in alphabetical order, in K to Q, this is the best part about this, is if K is less than Q, all right, that means more reactants are going to be made. The arrow points to the direction of the side of the reaction that it's going to move to. If you compare them in alphabetical order, K to Q. Okay? Because remember, K and Q are just a ratio between products and reactants. All right? So you're going to be forming either more reactants or more products, depending on whether or not how these guys compare to one another. Same thing with K and Q. If K is greater than Q, guess what? You need to make more products, because then Q will come up to K and reach equilibrium. Okay? Okay. Okay. All right. A lot of K going on here. All right. So, good? All right. So the deal is, typical sort of problem here is they're going to be like, all right, well, here's the situation. Our K value, so in this case, they're like, all right, synthesis of ammonia at 500 degrees Celsius. So this is Haber process. N2 plus H2 going to NH3. We need a 3 there. Okay, the K value for that is 6.0 times 10 to the minus 2. All right, so they give us the equilibrium constant. They're telling us, hey, this is the equilibrium constant. And they're saying, all right, well, which way is the reaction going to move to get to equilibrium if this is the case? So we don't know where the reaction's at. We don't know if it's at equilibrium. We don't know. So we have to calculate Q, right? And Q works the same way as K does. So it's products over reactants, okay? And that means it's going to be concentration of NH3 squared over concentration of N2, concentration of H2 cubed. All right, now I'm just going to plug the values in. Caller. So 1 times 10 to the minus 3 squared over 1 times 10 to the minus 5 times 2 times 10 to the minus 3 cubed. Square that. Okay, divided by 1 second minus 5 times 2 minus 3, and then we need to cube that. All right, I got a massive number. I wonder if that's right from what I did here. Yes. All right, so I got 1.25 times 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7. So if we compare these guys, K is much less than Q. So reaction will shift towards reactants. Yeah. Correct. Yeah, left is reactants, right is products. Yep. Mm-hmm. So the arrow pointed which way it's going to go. Okay, it's going to move back towards the reactants. Good. All right, so all you have to do is calculate Q, compare it to K, see where we're at. All right, so we'll do one more of those. I'll do the next one here. So Q, plug it right in. 2 times 10 to the minus 4 squared over 1.5 times 10 to the minus 5 times 3.54 times 10 to the minus 1 cubed. All right, so I got 0.060. So K in this point is equal to Q, right? So it's at equilibrium. We're already there. We're at equilibrium. Okay, that's what we're looking at. So same thing with the last one. You just have to calculate Q, compare to K. That's it. All right. Okay, so that's it for today.